So we've got a point 3 comma 4. Now if we were drawing that point 3 comma 4, that would be right there. It's on the terminal arm. Terminal arm is where an angle stops. We know that a standard angle always starts at the positive x-axis. It's going to stop, and it's going to be going through that point. So 3, 4 is on that, and our standard angle starts from the positive x-axis and goes to that terminal arm. We're going to call that angle theta. Now, if you have a point on a terminal arm, you can always make a triangle. Can you see that if I draw down from here and then over, that would make a right angle triangle? And what do we know about that right angle triangle? What lengths do we know? 4 and 3, right? Because it's going up 4, so we know that length is 4. It's going over 3, so we know that length is 3. Maybe you recognize this triangle. How many people recognize this triangle? It's a famous one. 3, 4, 5. It's one of the first ones with a squared plus b squared equals c squared, where all the numbers are nice. It's going to get me off topic right after this question. I'll talk about favorite triangles of mine in a second. Okay? But we already answered part A. Now, if you didn't know it was a 3, 4, 5 triangle, for part A, you would say a squared plus b squared equals c squared. That's a 2. 9 plus 16 is 25 equals c squared. Square root both sides. Now, normally when you square root both sides, you have to remember the plus or minus. But since we're dealing with lengths, it doesn't really make sense to have that as a negative 5 for a length of the triangle. So we just use the positive value. So there's part A. And of course, if you recognize the triangle, you could just write 5 right away. Part B, determine the primary trig ratios. Now this word primary, when they talk about primary, they're referring to cosine, sine, and tangent. Those are the primary ones. Next year in grade 12, we look at the secondary ones as well. So then you'll have secant, cosecant, and cotangent. But not yet. Secondary trig ratios. So the primary trig ratios. We look at this. What is sine of theta? Look at the picture. Right? Again, you might go back to your acronym to help you remember. SOHCAHTOA. Opposite over adjacent. Hypotenuse. Good. So sine will be opposite side would be 4. Okay? This is the ratio. 4 over 5 is the ratio. It's not asking us to find theta yet. It's just asking us to state the ratio. So sine of theta is 4 over 5. We can quickly say that cos of theta would be, should be quicker, 3 over 5. And finally, tan of theta, 4 over 3. Excellent. So those are the primary trig ratios. And finally, it says, determine the measure of theta to the nearest degree. You can use any one of these, right? Remember, when we want to find theta, right, that's when you're going to use one of the inverse functions, either sine inverse, tan inverse, cos inverse. So it doesn't matter which of these ones that you pick, you can find it. So someone said, let's use tan. We know that tan of theta is 4 over 3. The idea with the inverse is basically we need something that gets theta by itself. And what we've learned all the way through in all of our equation stuff is what you do to one side, you do to the other. Okay? So we need to undo this tan, get this tan out of here, right? When we had this, in this question right here, when you had c squared equals 25, how do you undo a square? You square root, right? We have to say squaring is a function. We have to do the undo function, do the opposite. The opposite of squaring is square rooting. Tan is a function. Tan isn't a number. We can't divide by tan because it's not a number, but we can do the opposite function. And the opposite of tan is tan inverse. Now, normally, you don't even write this on both sides, but if you did, because you're doing an opposite, those would cancel. And you get theta has to equal tan inverse of 4/3. And probably last year when you did this, you just wrote this step. But basically what you're doing is you're still doing the same thing to both sides, but doing the tan inverse will cancel out the tan. Just like here, the square root cancels out the square because they're opposite functions. So we go type this into our calculator. 53.13. Awesome. 53.13 degrees. Did it say to the nearest degree? So then to the nearest degree we would have theta is equal to 53 degrees. Okay, I said I'd get off topic a little bit. I'll tell you the questions that you can do for this one. I already assigned you question 3, 5, and 6 from before. So if you haven't done those, I have already said 3, 5, and 6. To that, you can add 4, 8, 9, 10, and 12. Okay, now, favorite triangles. No, this is good stuff. I want my favorite triangles to be on there. The first triangle that has nice numbers is the 3, 4, 5 triangle. A squared plus b squared equals c squared. Of course, you learned about similar triangles in grade 9. If you double all those sides, 6, 8, 10 is also a nice one. But that one's basically the same as the 3, 4, 5, so we don't consider it like different. It's not like a new one. The next one after 3, 4, 5, there's one that is 5, 12, and 13. No, you can just watch. What I'm going to get you to do is see if you can figure out a pattern. Okay? I'm going to draw the next one, 7, 24, 25. And then I'm going to leave things blank on this one and tell me what patterns you see and what you think will be the next. Well, we can draw. The hypotenuse, it has to be that they're all nice numbers, right? Let's look for patterns. We want to find the next one. What do you see?
9 for the side.
9 for the side. What are we, because the pattern is?
3 plus 2 is 5. 5 plus 2 is 7.
Just odd numbers on the side. So if this one's 9, then the next one after that will be 11. Good?
Yes.
What other patterns do you see? What do you see? Is the hypotenuse 40? No, it's not 40, but what pattern were you looking for? Tell me the pattern and we'll...
Wait, no, never mind. Sorry, I just can't. Oh, yeah. Is it 30?
Okay.
32. No, 33.
You can use your calculator to check. So 40 for what? The hypotenuse?
Yeah.
And how did you get that pattern?
Because 5 plus 8 is 30, and then you do that. Like 13 plus 12 is 25, so I just added another 4 on that.
Another 4 onto...
Like,
So you're saying that here
goes up by like another 4.
you're adding 8, then here you're adding 12.
Yeah, it's like the same. It's like the same as the last one.
So you next time you want to add 16, that'll make 41. That is the right number that goes there.
40.
And why do you think this one's going to be 40? So the pattern of seeing that it's one less. Okay, good. Does it, that is the right answer for that one. Let's see if that pattern works to find the next one. What would be the number here? 61, and this 60? Sure enough, that works. Okay? So someone noticed we're going up by 8, then up by 12, and going up by 4 each time on the hypotenuse, and it works out. Okay? Show you another thing that's kind of neat. These two numbers that were the last two that we had to find, those ones I've circled, what do they add up to? 9. Okay, so they add up to 9 in this one. What do they add up to in this one? 25. What do they add up to in this one? 49. What do they add up to in this one? 81. 121. This might even be a nicer way, perhaps, to find the next one. What is 13 squared? What two numbers would go here then? It's got to be 80, 85, and 84. And sure enough, it does fit the pattern of adding 24 the next time. But the pattern of how much you're adding and going up by 4s, although it works, doesn't help you find one really quick. This other way helps you see it pretty quick. I think that's pretty cool. That is one set of Pythagorean triplets that has a nice pattern. There are other sets of Pythagorean triplets. Probably the first one that doesn't fit this pattern is the 8, 15, 17 triangle, which if you check 8 squared plus 15 squared is 289, which is 17 squared. Pretty cool. And then you can try to find other ones and spend lots of time doing that. All right.